Hey everyone, today's concept is colors in computers. Have you ever wondered why the perfect red on your screen looks so dull in your print? This is because of the color science between them. Today we are going to go through this color science fundamental concepts. Color science is the fundamental concept that explains how colors are formed and represented in the devices and how they are reached to the human eye. Understanding different color models and chromaticity diagrams explains how this color science works, and we can understand how they are converted from being the displays and being in the paper's print. The color models are the techniques used to represent the colors in the computer displays. There are three major color models: the RGB model or the additive model, the CMY model or the subtractive model. The HSL or HSV model are also popularly known as perceptual model. These are the models that are majorly used to represent colors in the computer graphics. First up is the RGB color model. The RGB represents red, green and blue. This is the language of light used by the monitors, cameras and LEDs. It is called as an additive model because we initially start with the black, that is the absence of light, and start to add the light beams. Once we start to add the light beams, we will eventually start getting the color. Once we add all the light beams at the equal proportion to the highest, we get the white light. This is the language used by every digital color you see. All the digital colors in the display are just a coordinate within this 3D color cube. Next up is the CMYK model or the subtractive color model. Here CMYK represents cyan, magenta, yellow and key. Key means black. This is the languages of ink and pigments used in all sorts of printing. It's called a subtractive model because the ink absorbs light reflected from the white paper. That's why CMYK should be theoretically yield black, but whereas in real time it's muddy brown. So we add the K. The K means black to get the real pure rich black color. Also the technique used to printing is half toning. Half toning means printing tiny dots of ink on the paper instead of solid blends. Here we start from the true color and we initially concentrate to the black. This is how this model works. The last model is the perceptual model or HSV-HSL. Here HSV represents hue saturation value and HSL represents hue saturation lightness. These models are primarily used in softwares like Photoshop and video editing softwares to make color adjustments in situ. They are designed for human perception. Breaking down color by hue is the color of the tint. Saturation is the purity of the color, and value or lightness refers to the brightness of the color. It is great for making creative color adjustment naturally used in editing softwares. So far we have seen the color models. These color models are perfect for the separate platforms, as for the additive model for the displays and for the subtractive model for the printing stuff. So there won't be problem unless these colors are transferred from one platform to another platform. So when transferring color from one platform to another platform, we need a unified universal mapping technique to make these colors flawlessly transfer from one platform to another platform. That is where the chromaticity diagram comes into play. CAE chromaticity diagram. This horseshoe shape is a universal device independent map of color perception, showing all the colors the average human can see. It is a 2D map that plots only the chromaticity, the color itself, not the brightness. The curved boundary is the spectral locus, labeled with wavelengths in nanometers, from deep violet to deep red. The dot in the center is the white point or the reference weight. The closer is a color to the edge, is the more saturated the color it is. The closer the color to the center, the more white is mixed in. By drawing a line from white point through any color to the spectral locus, we can find the specific color's dominant wavelength. A crucial application of this diagram is defining the color temperature. The curved dashed line inside the Planck's locus is the colors an ideal heat object emits as it gets hotter. This is why we measure light in Kelvin. As you can see, low temperatures like 2700 Kelvin are warm, while high temperature like 6500 Kelvins are cool and bluish. This is essential for consistency in white balance. This is one of the most practical concepts in today's concept. As you can see, no device can reproduce all the colors on the horseshoe. The ability of a device to define the color is defined by its color gamut. It is shown by a triangle. The three corners of a triangle are the device-specific RGB primaries. This visually shows why Adobe RGB can display much more saturated greens and cyans than the smaller web standard sRGB triangle. If your color falls outside a device gamut, it must be compressed or shifted to the closest reproducible color. As for conclusion, the RGB model uses light to create bright saturated colors that often falls outside the printable CMYK range. The CI diagram is the universal reference that allows color management software to understand why they don't match and to correctly translate colors between two systems. If we want consistency, always check the color profiles. That covers the basics of color models and CI diagram. Now hopefully we have a solid foundation for better color decision. Thank you.